Hello and welcome once again to the exam solutions for A-level physics. This time we've gone for AS2 and it's a question from 2011, the summer exam in 2011. So let's get started, and it is a question on standing waves, and this is question 4. So let's read what it's all about. In a normal 6-string acoustic guitar, top string is tuned so that its lowest natural frequency is 82 Hz when the full length of the string vibrates. So figure 4.1 represents guitar, but only the top string has been shown. Part 1 of part A asks us to draw the first mode of vibration, the fundamental for the string. So the standard pattern of the wave, whenever we have a standing wave for a string, just zoom in a wee bit here, you have to learn this off. Simply just wave, something like this. There we go, and we can draw in the position of the wave half a cycle later. So there we go. That's what it looks like. Alright, then it says part 2 for us to label every node N and every antinode A. So an antinode is where the string is vibrating with the biggest amplitude. So we can put in our antinode A here. Okay, and our node is where the wave has zero displacement as the wave passes. So our ends are going to go on both the ends. There we go. Part B then. If the distance between B and M is 0.84 meters, whereas the wavelength of the first mode of vibration of the standing wave on the string, what we have here is the profile of actually only half a wave. We've got a crest here, and then it comes back to the rest position. So if that's only half a wave, if 0.84 meters is half the wave, then our wavelength for the whole of the wave must be twice that. So we're just multiplying 0.84 times 2, which is 1.68 meters wavelength. Part 2 of question B says to produce a note of a higher frequency, the guitarist places one finger at point X on the string. The string cannot move at that point, and the vibrating length is effectively reduced. He then plucks the string with another finger between X and B. The note obtained has a fundamental frequency of 328 Hz. Calculate the distance X to B. So we look, that's talking about saying that somewhere in here is point X, and the guitarist then plucks the string between B and X. So we're shortening the string, and we know that the frequency whenever it vibrates is 328 Hz. We have to calculate what that distance is. So it's the fundamental frequency, so it's going to have the same wave profile as what we have here. Okay, so it's going to be half of the wavelength. Now, what we need to do for this is to think about how the wave travels in the string, and the wave is going to travel at the same speed in the string as it is in figure 4.1. So for figure 4.1, we can work out what the speed is, and then we can use that speed to work out the length of the string to get us our second frequency. So let's go with that. So our speed V is what we're going to try to find first of all. We've got our frequency of 82 Hz, and we've got our wavelength of 1.68, and the equation we're using is V equals F lambda. So that's 82 times 1.68. This is equal to 1 137.76, but we're going to go for 138, rounding it up meters per second. So it travels the same speed in the second frequency that we have, and we're trying to find the wavelength for this second frequency. So our speed is 138 and our frequency is 328. So we're using v equals f lambda once again, and our 138 equals 328 lambda, and then lambda is equal to 0.42. Okay, now this in fact is double the distance that we need. If I scroll up to our picture of this again, our diagram, we have only half of the wavelength within the trapped wave for the fundamental frequency. So we need to divide that wavelength by 2. So the distance is going to be 0.42 divided by 2, which of course equals 0.21 meters. 0.21. The final part of this question, let's go up to part C, and it says guitarists are able to produce different modes of vibration on the same length of string by lightly touching the string. This creates a node at the point touched, but does not reduce the effective length of the string that is vibrating. So in figure 4.2, sketch the simplest mode of vibration that results when a guitarist touches the string at position F, and the distance FM is 0.2 meters, and the distance BM is 0.84 meters. So if we have a node here, and a node here, and a node here, then maybe just by looking at that you would imagine that there must then also be a node here. So what would the sketch of that look like if we had a node at all those places? Well, go up through here, we can draw in as well just what the wave might look like half a cycle later. Alright, so there we go. Just have a quick way look at the mark scheme. Top part there. What do we think? Tick.